Okay, so let me start. I'm talking about matching and merging now. And I'm showing you this again. So this morning I was talking about the Parton shower, so final state radiations from the hard interaction here, and also initial state radiation, and a little bit about hadronization. But this lecture now will be about how to best combine the matrix element calculations here, the fixed order calculations, and the Parton shower to get the most reliable results. And just a small recap on Parton showers, so what we learned this morning. So we start from a 2-to-2 scattering and want to dress this with extra partons to get an exclusive 2-to-n cross-section. And the exclusive 2-to-n cross-section would be given by this expression. So we would have the inclusive 2-to-2 cross-section here. This is like the folded PDFs with the matrix element of the Born process, integrated over the phase space of the Born level. Then for each emission, we have this emission probability here with the ratio of PDFs in it for the initial state radiation times the probability of not having resolved emissions above that scale. This is what was distinctive about the Parton shower. And then we have a product of this for every emission that we could have, always taking into account the no resolved emission probability here. And then we attach one no emission probability at the end, all the way down to the cutoff after all emissions have been generated. This is exclusive then. This is just the same way of writing it as I did it before. The only thing I introduced here is this capital F, which is the product of XF. So it's the momentum flux instead of the probability of extracting these partons. Just a little bit easier to write it this way. So the probability of not having resolved emissions was given by this exponential of minus the integrated emission probability. And as I said, if you expand this in orders of alpha s, that gives you corrections to all orders, but it only includes the correct terms for the double log, or if you have alpha s running included, the leading log. So it corresponds to resummation in that sense. This ratio of PDFs, as I said, is only included for initial state radiation. And these no emission probabilities allow us to actually get exclusive predictions. So the prediction for having a jet, but no other hard jet in an event. This is what I call exclusive here. So I was talking about unitarity, and I want to go a little bit more in depth because that is helpful for this lecture. So instead of looking at it entirely, I will do a fixed order expansion to order alpha s square. And then starting from this formula here, if we expand this in orders of alpha s, we will have contributions from the emission probabilities here, but we will also have contributions from the no emission probabilities. Remember, this was just exponential of minus the emission probability. So for the zero emission case, the only thing we attach here is the no emission probability from the maximum scale to the minimum scale here. And expanded, this is just the exponential expanded. This is just 1 minus emissions probability plus emission probability squared here. And if we look at the exclusive one-jet cross-section, what we have instead is the Born cross-section times the emission probability once. And then we got this product of two no resolved emission probabilities. So one above the scale of the emission and then one below until the cutoff. And this would give these two alpha s terms. And the two-jet cross-section, which at order alpha s squared doesn't include any Sudokov, because that would be at higher orders in alpha s, this would correspond to these two emission terms here. And what we see if we expand here in orders of alpha s, oh, sorry, I didn't mention, I include some factors in the emission functions here to just make it more clear. So everything is included basically, but the factor of alpha s, to make this more obvious. So what we get here upon integration is that these terms cancel, the ones I color-coded here. So upon integration, this is a minus contribution, this will be a plus. So these two will cancel. Then if we integrate over the one-jet contribution, get this integral here. So together with this one, these two will cancel that one. And this term here will cancel that one. So what we end up with, if we integrate over all the differential exclusive samples here and sum them up, is the inclusive cross-section, which we started with. And that's the unitarity of the Parton shower in terms of an alpha s expansion. But already now we see that the one-jet cross-section that the Parton shower will give us is approximated by the leading order, this Born sample times the emission probability, which was derived from the collinear and soft limit. So the one jet exclusive cross-section given by the Parton shower will be an approximation here. And we want to improve this description in matching and merging. So slight comparison about the benefits and drawbacks of matrix element calculations and Parton showers. So matrix elements are fixed order expressions. So to a fixed order of alpha s, they have all the logarithmic contributions you could think of. So there's no soft or collinear approximation for matrix elements. And they are good to describe hard jets due to the fact that they don't make this assumption. And so they are good for emissions at high relative PT. But you can sadly only do matrix element calculations for a few emissions because you just run into problems. It's getting too complicated and computationally expensive. The Parton showers, on the other hand, are exclusive predictions with approximate emission probabilities. They are always finite. They can produce any number of emissions. That's very useful. But for large and hard emissions, it will be an approximation. So only in the soft and collinear region, this Parton shower approximation is reliable. So the goal of matching and merging is then to combine the strength of matrix elements and Parton showers. So we want to describe hard emissions by fixed order predictions. And soft emissions should be approximated by the Parton shower, also including these probabilities of no resolved emissions. So this is an outline of what I'm talking about. There's different ways in which these combinations can happen. I just want to, one of the goals of this lecture is for you to understand what the difference between matching and merging is. So the first scheme, that is the oldest thing that has been done, is matrix elements corrections. And the idea behind that is to correct the emission pattern of the Parton shower process dependent for the very first emission. So if you're interested in E plus E minus going to jets, you could just implement the correct matrix element for the first emission and generate emissions according to that instead. And that would be a matrix element correction. But this is process dependent, so it will be quite painful to iterate this process for all the multiplicities you're interested in because it gets very complicated. So what you do instead is multijet merging. It means you rely on some matrix element generator to generate samples with different jet multiplicities and then add them together in a very clever fashion to avoid double counting. So this is merging. Usually you use, in leading order merging, you would just use leading order samples with additional jet emissions and then combine them in a way that I'll explain in detail. So this is what I'm focusing on in this talk. So what you can do as well is NLO matching, and that is basically combining higher order calculations for the matrix elements, so NLO calculations with a Parton shower. And similar to this, there will be problems of double counting, so this is why you need to be careful in this context. And finally, you can also combine multiple samples of NLO correct jet cross sections, and that would be NLO matching and merging combined. But I'm not talking in detail about this. So the matrix element corrections. I mentioned it already. The goal is to correct the emission pattern of the Parton shower, because we had the soft and collinear approximation built into the Parton shower, but we want a better approximation. So for the first emission, typically the matrix element expressions are not too complicated. So instead of using this approximation, we can generate this radiation according to the correct matrix element. So instead of using this, this approximated emission probability, we take the ratios of the matrix element with the radiation over the one without the radiation as the emission probability. And this will then correspond to the correct matrix element distribution. So to the correct fixed order description of this branching. And I just include the differentials here. So you might end up with Jacobian factors depending on how you parameterize your splitting variables. So just keep that in mind. But in this notation, I'll just include them in the matrix element corrected splitting kernels here. So this is old, but it is very good. So by building this, it is very efficient. It comes natural in the language of the Parton shower. I talked very briefly about the Sudokov-Vito algorithm, But basically, you can use the same method when implementing matrix element corrections. The only thing you change is the probability with which you accept emissions. So you have a reliable overestimate, and you propose emissions as you did before. Only the probability of accepting this will be corrected with the correct probability. So this is easy to implement, but it's very difficult to generalize. You don't want to build this in by hand for every multiplicity and every process that exists. But people are working on this. So the Vinci Parton shower, for example, exponentiates a +1 jet matrix element, even at NLO. So yeah, people are working on this. So having a look at the unitarity again, you will see this comes back again and again. So this is the same formula. We have the alpha S expansion of the exclusive cross sections of no additional jet, 1 additional jet, and 2 additional jets, or partons here. And these matrix element corrections just correspond to replacing this emission probability with the correct one, the more precise one. And this happens for both the Sudakov vectors and for the actual emissions. So just for the first emission, but still this will all cancel. And if we integrate over all of them, we still end up with a correct inclusive cross-section. And this happens to all orders in alpha S. And a good thing about these matrix element corrections is that you can do that all the way down to the cutoff of your Parton shower. Because you implement it in the Parton shower, there's no problem with this. That's a very nice feature that is not given in merging, as you will see. So just an illustration, I stole a slide here. It's very nice. So in the process of glue-glue fusion to Higgs at leading order, this is an order alpha S square leading order, the Higgs will be aligned with the beam because there's nothing to recoil against at leading order. Only at next to leading order, if you allow for 1 emission of a jet, there's a PT of a Higgs, because then it can have something transverse to the beam to recoil against. So the PT of the Higgs in this process is a very good observable to check what effect the first jet emission has. And the matrix element will be divergent for softened collinear in the softened collinear region, but it will be very precise here in the large PT region. Whereas the shower is a good approximation taking into account the Sudakov behavior at low scales. It will still be rather reliable in this mid-PT range here. And well, due to the unitarity of the shower, it will always integrate to the correct inclusive cross-section. But at very large scales, due to the fact that the Parton shower was based on a collinear approximation, this will actually be a very poor description. And what we want is now a description that gets this tail right, but still has the physical behavior of the Parton shower towards low scales. And that is exactly what matrix element corrections do. They just fix the radiation pattern of the Parton shower in the first emission to this correct result out here at large PT, and still have this correct suppression at lower scales. So now we want to iterate this. We want to describe 1 jet precisely according to the fixed order term, but we also want to do that for a 2nd jet, a 3rd jet. So the naive and wrong way of doing this, I say that, wrong, is to just generate samples using MudGraph, for example, for a given process, process plus 1 jet, process plus 2 jet, attach a Parton shower to each of them, and then just combine the samples. But this will not work because all these samples are inclusive. So we will end up double counting. And this is an illustration I took from an introduction to a QCD from Scans. So the matrix element, so if we plot loops and legs here, so additional jets will correspond to going in this direction, and loop corrections at NLO will correspond in this direction. But we are talking about leading order here, so we will not do matrix element calculations at loop level. But still, as I said, the Parton shower approximates virtual corrections and also the radiation pattern. So this is yellow here. So at the lowest order, we will have the Born process correctly based on the matrix element, and then we get an approximation based on the Parton shower. But if we add another sample now, we would generate events using matrix element generator of 1 additional leg, where we do some cutoff in phase space to regulate divergences that we will end up with, run the Parton shower, we get, again, virtual and real approximations here. And this will lead to double counting. And this is the basic problem in merging. We need to avoid double counting. So whatever the Parton shower approximates should be subtracted when we add in, or at least regulated when we add in further perturbative input using matrix element samples. So basically, what we need to do to find an exclusive description without double counting is to solve this issue by dividing the phase space into a hard and a soft region. And then the goal is to describe the radiation pattern in the hard region using the matrix elements, the correct expressions, and then attach as much radiation activity as we want in the soft region where the Parton shower is a good approximation. And we need to do some sort of cut to separate these two regions. That is the merging scale cut. We need this because we can't just do merging, we can't just do matrix element calculations all the way into the divergent regime because it diverges. So it's not reweightable. So, and then to make these samples exclusive, we need to apply no emission probabilities as the Parton shower does it, and also some scale-dependent ratios, as I will explain later. So the basic paradigm is to reweight these matrix element samples the way the Parton shower would have generated it, because the Parton shower is what makes them exclusive. And below this cut in phase space, we can then just attach the normal Parton shower to generate further soft emissions. And obviously, there's some issues with this approach. So we introduced a merging scale, but this is an unphysical parameter. We could have chosen it wherever, and we don't want our results to depend on the merging scale. So that's a problem. Then also, the merging scale might not be defined in the same evolution variable as the shower. So this is a slight complication that we might have to deal with. And this procedure might also break the unitarity of the shower. So by correcting the radiation pattern of the shower, you might end up with a situation in which the integrated cross-section, the Born-level cross-section, has actually changed due to the changes you introduce. But that depends on the merging scheme you use. So as an illustration, for a plus or minus going to QQ bar plus up to 3 jets, this is what I plot here. What you want to get is the red curve. That's the total curve. And what I plot here is the jet separation, E plus E minus. So this would correspond to 3 well-separated jets, while this is 2 collinear jets here. And as we see here, the blue curve is the Born matrix element, which is only showered below the merging scale then. So all these collinear emissions would be generated by the shower and contribute entirely to this. But as we go to higher scales, higher separations, the other samples kick in and describe these events. And adding these up in the correct reweighted way will then lead to the correct total curve. We can look at the same observable, but the separation between the 4th and 5th jet. And there we see that the plus 3 jet sample describes this hard tail exclusively, only this one. And then we get a transition between the samples, and the very soft ones are described by the Parton shower emissions on top of the lowest multiplicity sample, mainly. So we need reweighting, as I said, but in order to reweight with no emission probabilities and with scale-dependent ratios of alpha S and PDFs, we need the emission scales at which these splittings would have taken place. That is a crucial ingredient to doing this and to rendering these multiple samples exclusive. And there's basically 2 ways in which we could find a Parton shower history. And the first one is to apply a sequential 2-to-1 jet algorithm to reconstruct scales and then apply these scales for no emission probabilities and scale-dependent ratios. The other way is, as I explained this morning, in a Parton shower, you have 2 to 3 emissions, basically, because you have some recoil scheme. So to be equivalent to what your Parton shower does, what you would need to do is to invert the Parton shower and do 3 to 2 clusterings with the reshuffling of momenta to get the kinematics right. So this is considerably more complicated than this one. And you also need to reconstruct all the possible histories that a Parton shower could have chosen and then choose one according to the splitting probability in the Parton shower. You also need to involve the kinematics. But in the end, you will have a procedure that corresponds directly to what the Parton shower would have done. So it fits this picture of what would my Parton shower have done to render this exclusive precisely. So just an illustration, if you have a matrix element with two, so quark, anti-quark, and two gluons in the final state, this clustering would then give you a history telling you where these came from and at which scales they were emitted. 3 to 2 clustering? Yeah, so basically if you, let me find some chalk. So in a jet algorithm, what you do is just combine 2 partons into one. So you have some partons and you start finding close by partons and you would just cluster those into a jet. But as I said, in a Parton shower where you have dipole-like recoil, you would always have some splitting parton plus some recoiling parton, and this corresponds to a 3-particle thing. And then you would recluster this emission that took place to form the original parton here, but you would also need to rescale this slightly to remain on shell for all the external parton lines. And that's what this 3 to 2 clustering corresponds to. So, yeah, where do I put this? So an illustration in final state radiation, that's always a little bit easier than initial state radiation, so that's what I started. What we want to do is we want to take these matrix element samples without additional emissions, then with additional emissions, but they're all inclusive and with up to 2 additional emissions. And if we want to calculate the expectation value of some observable, we need to integrate over the phase space, evaluating this operator that defines our observable on the Born sample with some clever reweighting to render it exclusive, then also on the 1 emission sample and the 2 emission sample. And the weights are the weights that the Parton shower would have put when generating this. So the Born sample would be reweighted by the no emission probability above the merging scale to make this exclusive. So we want the probability of having just this final state, no further resolvable emissions. Then for this one, we would have the no emission probability down to some scale. Then we would have 1 emission. Parton shower would have generated 1 emission, but it would have used alpha S evaluated at this emission scale, whereas the matrix element generator will have used an alpha S at the fixed renormalization scale. So we need this ratio to take the difference into account. And then we have a no emission probability all the way down to the merging scale. And for the highest multiplicity, it's the same again. We have no emission probabilities down to some scale, rho 1, then an alpha S ratio to take into account the difference in the value of alpha S that the shower would have used. No emission probability again this ratio. But if this is the highest multiplicity that we end in by a matrix element, we will not have the description, the matrix element correct description of 3 or more jets above the phase space cut. So there we would allow the Parton shower to radiate further. So this last pseudocurve factor is missing in the highest multiplicity sample. It's just a subtlety to keep in mind. But of course, we are interested in PP collisions, and there's a lot of initial state radiation as well. So the situation is a little bit more complicated in the case of initial state radiation. So if we take this, this configuration here, so this is where the hadrons sit, then we have some PDFs describing the probability of extracting a given parton from the hadron. And then this, let's assume this is gamma or Z going to E plus E minus, for example, so that there's no shower here. But we have an initial state gluon radiation and then splitting into a quark pair. This is just an example. It could be whatever. So if we ask our favorite matrix element generator to give us an exclusive cross-section for this, so give us the matrix element description, it would use this full matrix element for this state and fold it with the PDFs of extracting these hadrons, these partons, from the hadrons. But if we use the Parton shower to generate this from this, starting process here with just the QQ bar in the initial state without an additional gluon, what the Parton shower would have done is to start out from this, just this process, then we would calculate no emission probabilities down to some scale, then it would happen to emit some gluon here with the correct PDF ratios in it, according to the splitting probability in the Parton shower. Then further, no emission probabilities corresponding to all the legs, the gluon, until we reach the scale of the second emission here. Again, alpha S, the splitting probability, and then if it's exclusive, also if it's fully exclusive, also the no resolved emission probability down to the merging scale. So what we want to do now is to find weights that make inclusive matrix elements that come from a matrix element generator exclusive as if the Parton shower would have generated them, to avoid double counting. So if we just compare these two expressions, what we end up with is a product of weights. So we got alpha S ratios corresponding to each splitting here, using then the scales that the Parton shower would have used to generate these splittings. We get PDF ratios for every internal momentum fraction that occurs to take into account the scales here. And then for the external legs, we might end up with additional PDF ratios if we had a fixed factorization scale when we generated the matrix elements. But that depends a little bit on the details. And we have the product of no emission probabilities for all the legs involved in this process. So applying these weights will give us the exclusive cross-sections. But to get them, we need some clustering, as I said. So just to summarize how the multijet merging algorithm in general would work. So in the first step, you would calculate the inclusive cross-sections for some process of interest, plus n partons, with some kinematic cut on it to regulate the divergences in the matrix element generation. Then you would cluster according to a jet algorithm or by finding the Parton shower history. And to get the scales that you need for no emission probabilities and scale-dependent ratios. And then in the next step, you apply these ratios and the no emission probabilities using the scales that you found. And if you are at not the maximum multiplicity of the matrix elements you include, you would also attach a no emission probability all the way down to the merging scale. At the highest emission, the highest multiplicity sample, you would allow the Parton shower above the cut to also radiate further. So now I will go through some different schemes of multi-leg merging that can be found in Parton shower programs. And the first one that was implemented is CKKW merging. And the clustering here is done according to a KT-jet algorithm. Might be modified slightly to only cluster allowed flavor configurations. And then you apply analytic pseudocurve vectors. They are very precise. And it's very nice to write this down. And you apply those as no emission probabilities. And then you need to perform truncated showering. So since the Parton shower evolution variable is not necessarily the same as the one that is used by your jet algorithm, you somehow need to deal with emissions that the Parton shower generates at rather hard scales as measured in its own evolution variable, but that are below the cut that you imposed on your sample. So I'll not go into detail on this, but this is a subtlety that comes up when merging. So the advantage of this method is clearly that it's a nice theoretical treatment. You get these analytic pseudocurve vectors. You can actually write down what you're doing. It's always nice to understand. But it requires a dedicated Parton shower implementation to deal with this showering here. And there's a mismatch between the analytical pseudocurve and the Parton shower, the no emission probabilities that the Parton shower generates, because the Parton shower is just not as correct theoretically as the analytical pseudocurve is. And this was the first thing that was implemented when Sherpa came up, the early 2000s. Then a very similar scheme is the CKKWL merging. And the crucial difference here is that you rely on the Parton shower more extensively. So instead of doing a KT jet clustering and applying analytic pseudocurve vectors, what you do is you cluster according to the Parton shower history. So you do this inversion of the Parton shower history to get your states and find out how the full cascade looked like. Then you generate no emission probabilities also using the Parton shower. So you feed your Parton shower partonic configuration and then just run it to see if it would have emitted or not. And this is how you would estimate your no emission probability in this scheme. And this is done step by step for each intermediate step in the Parton configuration. And then, yeah, you can veto if you emit, or just keep emissions below this cut. And this method has a very nice agreement between the Sudakov and the shower by construction, because you ask the shower what the Sudakov is. So the estimated Sudakov factor is the same as the no emission suppression that the Parton shower generates. So this reduces the merging scale dependence of the scheme. And if you define your cut here in a very similar way as the evolution variable in your Parton shower is defined, this will also be a simple veto procedure. So you would not have to deal with additional radiation on intermediate lines. But you can if you have a mismatch between this definition of the cut and the evolution variable of the shower. Again, this requires a dedicated Parton shower implementation to find these histories and get these weights. But this is very popular. So this is implemented in Sherpa, in later versions of Sherpa. It's in Pythia, and it's also in Reweight. And then another scheme that you could use is the MLM merging scheme. So the MLM merging is basically the simplest to implement way to estimate a Sudakov suppression. And it's a little inverted in philosophy compared to CKKW and CKKWL. Because what it does is runs a shower on the matrix element state without doing prior reclustering. But it starts from the highest scale in the process. So it would just run the Parton shower on the external leg configuration of the matrix element. And then it would perform a jet clustering. And based on this jet clustering, it would decide which events to reject, because if the Parton shower emitted hard emissions that are not reclustered to the hard partons that you started off with in your matrix element. So since you don't reconstruct the history here to find the no emission probabilities, the Sudakov factor doesn't correspond to the correct internal structure of your event. It corresponds only to the final partons. So this is an approximation, but it turns out to be pretty good. And it is very simple to implement, because you just need to run your shower on the matrix element and then apply a jet clustering. But you don't need to deal with the details of the shower. You can do it with whatever shower you like. And yeah, the drawback then is that the Sudakov suppression is not exact. So you get a mismatch with the shower, and the further down in resolution scale you go, the larger this mismatch might be, because there the Sudakov suppression is more intense. So just to make this a little bit clearer, so if you ask your favorite matrix element generator for a matrix element, you just end up with these external lines here. You don't know how this process looks internally. So MLM would first shower this all the way from some hard scale to the lowest scale, but just using these external lines here. Then it does jet reclustering to estimate the Sudakov factor. And the resulting no emission probability, as I said, will correspond to these 4 quark lines, basically. If you do CKKWL, the first thing you do is reconstruct the Parton shower history. So you ask your Parton shower, how would you have generated this event? You get this internal structure, and then you do a trial shower for each internal configuration here until the first emission. Then you do a trial shower here to find out if there would have been an emission, and in that way estimate your Sudakov suppression. And the resulting Sudakov suppression would first correspond to the no emission probability of these 2 quark legs, then also this gluon, and then finally of the external quark legs going down to this merging scale cut. So this is different, as this is an approximation. And if we take a look at the unitarity, so yeah, this was 3 different schemes that are implemented, and for all of them you can look at the unitarity of the multijet merging. So that was what we started from. The Parton shower should not change the inclusive cross-section. It should just change the, it should just dress the event with additional radiation. But if we do this merging, so we replace the radiation pattern of the Parton shower with the correct matrix element expressions here. But we still ask the Parton shower to give us the no emission probabilities. So this is red here. without this correction, then this cancellation in all orders of alpha s is broken. So what we end up with is a change in inclusive cross-section by including higher multiplicity samples. And then everyone needs to decide for himself whether this is reasonable or not. So, I mean, changes are beyond this order in alpha s. So we are still at leading order, but it's kind of inconsistent to do it this way, to replace these but not replace these in the pseudograph suppression. So a way to fix this is using unitary merging. So it is based on the CKKWL scheme. It's very similar to that. But what you do is you restore Parton-Schauer unitarity by using that the no resolved emission probability is 1 minus the integrated emission probability, but with the correct matrix element emission pattern. So if we look at the exclusive cross-sections again, but this time not expanded in orders of alpha s, we would have the inclusive 0 additional jet cross-section here, times the pseudograph suppression to make it exclusive. Then this would be the 1 emission case, again with 2 pseudograph factors. And now if we apply this formula to this, what we end up with is 1 minus, and then the matrix element corrected next splitting. So if you have a close look at this, now these orders, these terms here cancel. And we get back the unitarity. Doing it in this way, we will not change the inclusive cross-section, because if we integrate over all samples, these terms here will cancel. And we are back at the original inclusive cross-section that we found at lowest multiplicity. So just to illustrate the difference here, so this is still CKKWL reweighted samples, and instead of having this last pseudograph in the chain, we use these 1 minus the matrix element sample reweighted instead. And we can still attach the normal Parton-Schauer below the merging scale. But now what we observe is the cross-section of the merged sample divided by the cross-section of the inclusive sample changes in CKKWL depending on the merging scale that we use. But in unitary merging here, we will be on this line. But you also see that the error, the statistical error of the samples here is different. So in UMAPs, due to the fact that we have a minus here, what we actually do is we take every second event, integrate it one step using this procedure, and subtract it from our diagrams, from our histograms. So there's a huge cancellation in the histograms happening, and the statistical power of our sample is reduced significantly. So for the same number of generated events, this unitary merging will have large statistical uncertainties, whereas CKKWL was quite precise. But on the other hand, we always remain with the correct inclusive cross-section, or at least the inclusive cross-section that the lowest order result gave. So just a few words on NLO. Basically, we face the same problems when going to next to leading order matrix elements. And you will hear details about this in the NLO lectures tomorrow. But basically, we still got the problem that the Parton-Schauer can emit, can radiate further emissions that are already approximated by real emission matrix elements when going to next to leading order. In addition to that, the Parton-Schauer also approximated virtual corrections that are included in next to leading order calculations. So there's an additional double counting problem. So the topology, you saw this already for an NLO calculation, is basically the integral over the Born contribution, the virtual corrections, and the real corrections. So this is an additional radiation, that is loop corrections. But the problem is that V and Bn plus 1 are individually infinite, and only the sum of the two will be finite. So there's universal subtraction methods to actually be able to numerically generate NLO cross-sections. And what you do there is you add a 0, basically. So you add an integrated term to the virtuals to render this finite, and you add a subtractive term to this sample to make this finite. But the observable dependence here, so the multiplicity of the state at which you evaluate your observable will be n in both cases. So when you fill your histograms, you will not evaluate this at the differential phase space point where you're at, but you would use this 3-to-2 clustering to evaluate here instead. So if you want to generate events, you need to have a finite contribution for separate observable dependencies here, and this is still not given here. So for the total cross-section, this would be good enough, but if you want to generate events with a Born topology and a real emission topology, you need to introduce a shower subtraction. And the basic idea here is that you want to attach a shower to your Born cross-section, and instead of writing this observable here, we attach a Parton shower. So this is basically a functional describing what the Parton shower does. So it has a no emission probability of keeping the state that you are at, so without emitting a further, generating a further emission, plus a certain chance to have one emission. So no emission above, then one emission, and then you iterate the procedure. So you could write what the Parton shower does in this formula, and if you expand this, you will get this integrated emission probability as the first term in the expansion of this pseudocov. But since this is a no emission, no resolved emission probability, this is still the observable with the dependence on the n Parton phase space, right? We didn't change the state. Whereas this term here has the n+1 phase space point. And when we apply the Parton shower on the Born sample, we will get order alpha s contributions. And clearly, these spoil the accuracy of our next to linear order calculation, because that NLO calculation is already supposed to get right all the terms of order alpha s. So subtracting exactly this contribution that the Parton shower gives on that sample, we end up with this modified function, equation that describes the expectation value of an observable. And so with the shower subtraction, it looks like this. We have the Born, the subtracted virtual, then we have the shower virtual and the subtraction, again on n Parton. The observable dependence here is n Partons, as it is here. So this corresponds to a Born cross-section, basically. And then we get this real minus shower real contribution. And since the divergence structure of the Parton shower is the same as the one of subtraction terms that you get in NLO calculations with subtractions, these are now separately finite. So these altogether are finite, and these are finite. That means we can actually generate events of a Born and a real configuration from this. Then the pseudocov suppression of this method still agrees with the Parton shower prediction, because we didn't change the Parton shower here, right? It's still the same Parton shower that we applied at the beginning. A drawback, it's not a drawback, but you need to keep it in mind the distribution is only correct if we actually run a Parton shower on it. So if you generate matrix elements with AMC at NLO, at NLO precision, it will include these Parton shower counter terms. And only when running the Parton shower, the effect of the Parton shower on this bit here will cancel these additional terms to give you the correct NLO result for the Born and the real configuration. But this last line is a little bit nasty because you got a minus again. So you will have a cancellation of events. So statistically, that might be a problem if there's a lot of events on both sides of this. So this can lead to negative events. And you need to implement this method for every Parton shower separately, because you need to know what the Parton shower is doing to subtract it in the first place. But this was automated in AMC at NLO. And what AMC at NLO then does in general is basically give you a smooth transition between the correct real emission pattern at large PT scales and the Parton shower description at low PT scales without changing either of them. So that's very nice. There's an alternative method. So if you are sad about these negative weight problems here, what you could do is correct your Parton shower emission spectrum for the very first emission. That basically corresponds to a matrix element correction of this emission. And then this third line here just vanishes. And what you end up with is the Powac method. I don't go into detail here, but this will be without the negative weights. But you will modify your shower if you do this. So this is what I mean by HI, the hardest improved shower. For the first emission, you generate the correct real emission pattern instead of the shower reel. So you get less negative weights, that is an improved efficiency, but the hardest emission is modified. So the description that you get is still NLO correct, but it will be different from the one that you had in AMC and NLO. And the implementation here, since you do this correction, is process by process, because this is process dependent. And yeah. Now, but the advantage then is that it's not shower specific. So you can implement this, you can implement the first emission in the method, and then you can attach whatever shower you like, basically. Yeah, I don't go into more detail here, but as I promised in the beginning, there's also NLO matching, so NLO correct jet descriptions merged. So you can do multiple NLO calculations for additional jet patterns and then merge these samples. And the method is very similar to leading order, just that you need to avoid double counting again. So it's very technical, but what you basically do is subtract orders of alpha S in effects on samples that you don't want using Parton shower unitarity. It's a lot different between these methods. So there's the unlobs methods, that's unitary again based on UMAPs. Then there's MinLo, multi-scale improved NLO. That's based on PowHack. Then there's the FX method. That's based on MC and NLO and then does something very similar to the MLM method, but it takes into account the initial structure, doing something CKKW-like for no emission probabilities. And Vincia, I mean, this is not multi-leg merging at NLO, Vincia, but it is NLO matrix element corrected Parton shower. So what it generates in the end is pretty similar to what PowHack would do. And if you do NLO matrix elements successively for also the second emission, what you end up with describing is pretty similar to this method. Okay, and then current developments in this field is, of course, improving these methods, but then also getting the NNLO right for the inclusive cross-section while still matching to Parton showers. Then improved uncertainty estimates. I didn't talk at all about uncertainty estimates, but that's very important because you need to know how precise or how accurate your calculation actually is. And then something that would also be nice is to actually match the NNLO matrix element calculation with NLO Parton showers. So that might be a next step in this direction. And this brings me to my summary. So matching and merging, the goal is to combine matrix elements and Parton showers. And the problem is that Parton showers already contain singular terms of higher order matrix elements. And when adding these matrix elements explicitly, we need to subtract what the Parton shower did, or at least regulate it using no emission probabilities, rendering it exclusive to not double count contributions. So basically, 3 ways to go. The first one is matrix element corrections, the oldest scheme. You just correct the emission pattern in the Parton shower. It's hard to iterate because it's process dependent, but there's developments and you can do it to higher multiplicity and also at NLO. Then we got multijet merging, where you combine multiple leading order matrix element samples by reweighting to make them exclusive. You need to have some merging scale cut in this method to separate phase space regions and deal with divergence. And there's different schemes available. So I discussed CKKW, CKKWL, MLM, UMAPs, basically. And then you can do NLO matching. So you need Monte Carlo subtraction terms to do this, to do NLO matrix elements plus Parton shower. There's basically 2 ways to do it, MC at NLO and PowHack. And this can then also be combined with merging schemes at NLO. And this is what you actually want. So whenever you can get it, if you look at multiple jet cross-sections, then to get the most precise answer, you would want to do NLO calculations and combine it with higher multiplicity NLO calculations to get the best description. So that's it. Thank you.